So we have finished Fourier series. Remember, in this chapter, we started Fourier analysis in general. So when we talk about Fourier analysis, usually we're talking about two main concepts. The Fourier, so when we talk about Fourier analysis, usually we talk about Fourier series and then Fourier transform. So remember, the Fourier series was mainly about periodic functions. So if you have a periodic function, then you have something called Fourier series. Now we discussed all, I think we discussed all related methods to periodic functions and the visualization of Fourier series, its geometric meaning. We applied it to obtain certain quantities that we can't do any other way. Now, what about Fourier transform? So today we're starting the new concept, the Fourier transform. So that's our new title. So Fourier transform. For students studying this course, Engineering Mathematics 2, remember in Engineering Mathematics 1 you studied something called Laplace transform. So the term transform is not a new term for you. You used it already, and you will see some kind of similarities between some kind. I'm not saying they are similar, they are completely different, but there are some aspects of comparison. So remember, for the Laplace transform, you started with a function f of t, you defined the integral from 0 to infinity, f of t e to the minus st dt. That gave you something called Laplace transform. We usually denote it by big F of s. So you start with a function in terms of t, you convert it to a function of s. Usually the t represents the time, the s represents something else, maybe the frequency. So we say time space, frequency space. Now what is the Fourier transform? So we're still talking about Fourier, and I'm trying in this video to make a little about the big picture of the Fourier transform. So we will be writing the definitions, but also we will focus on when these definitions work, when does the Fourier transform exist. We didn't do this idea in Fourier series, but at this moment I think this is the more convenient time to discuss these concepts after maybe comprehending everything related to the Fourier series. So the first thing in Fourier transform is that you have a function. It's a real valued function. It's from R to R. So let f from R to R be an integrable function. Now, what do we mean by an integrable function? Now, in some textbooks, you will see that the function is absolutely integrable. So some books write it integrable, some write it absolutely integrable. For mathematicians, the two concepts are the same. So the function is integrable if and only if it's absolutely integrable, and this is the big theory of Lebesgue integrals. But for the level of this course, I'm going to write let f be an absolutely integrable function, and I will explain what that means, okay? And we will explain also if periodic functions, because we're still doing Fourier analysis, and usually when we hear the word Fourier, we remember Fourier series, we remember periodic functions. So it's a natural question to ask if the periodic functions are absolutely integrable functions. We'll discuss this. So imagine you have an integrable function on R, of course. Then we define the Fourier transform. It's Fourier transform by f hat of omega or w equals 1 over root 2 pi integral from minus infinity to infinity f of x, if we use x, e to the minus I omega x dx. So this is our definition. Again, like at first glance, when you look at this definition, it's somehow similar there are some similarities between this and the Laplace transform. The Laplace transform was the integral f of x e to the minus x dx from 0 to infinity. So now we have basically two differences, from minus infinity to infinity instead of 0 infinity. Then minus sx, we have an extra I in the definition of the Fourier transform. Now, why is the Fourier transform defined this way? We'll see this. Okay, I will make one particular video on how to obtain the Fourier transform definition from the Fourier series definition. And please, I like to have things organized, and I like students to have the picture, the full picture in their minds, how we obtained everything. So if you remember, when we started the Fourier series, we started with a trigonometric polynomial. Then from the trigonometric polynomial, we found the formulas for a node, a and bn. Then from that, we moved to any periodic function to obtain the Fourier series. Then from that, from the a's, the a node, b, n, and bn, we obtained the complex Fourier series. So I like this picture to be complete, and then I will show you, hopefully I will show you how to obtain the Fourier transform from the complex transform. So to have this complete picture in your mind is very essential for you to understand what's going on. Also, I will make my best to have another video on visualization of the Fourier transform. So how do we understand the Fourier transform? I hope, I'm not a communication engineer, but I hope I will learn some signal processing stuff to show you some relations between the Fourier transform and how it is applied in signal processing. This is a very, like, one of the most interesting applications of Fourier transform. Okay, so this is our definition of the Fourier transform. So before doing any examples, I like to have some comments. So comments, remarks, call them anything you like. So the first thing, what do we mean by saying that a function f is absolutely integrable? So what we mean by this is, let's say a solution is not a big deal, okay? It's better maybe to write answer, right? So when we say the function is absolutely integrable, what we mean is that the integral from negative infinity to infinity, the absolute value of f of x dx is finite. So the idea, this integral on the left, this integral is an improper integral. Now, as an improper integral, you can have it finite or infinite. You need to discuss the convergence of the improper integral, and it is very possible that the improper integral is divergent. Now, when we say the function is absolutely integrable, we mean the integral of the absolute value is finite. What's the geometric meaning of this? How do we understand this? So, for example, if you draw the function, the simple function, like y equals x. So y equals x is a function of, like, one of the most simple functions. And if you try to integrate from negative infinity to infinity, the absolute value of x dx, I think that it's very clear, because the integral of the absolute value basically is the area between the function and the positive x-axis. And for the function x, I think it's very clear, without doing any kind of computations, that the integral is infinity. So basically, it's like we are saying that the function x is not absolutely integrable on the real line. If you integrate it from negative infinity to infinity, the integral is infinity. So this improper integral is not convergent, and that violates the definition of the absolute integrability. For example, if you look at another function like 1 over x. Of course, 1 over x is not defined at 0. You can define it to be anything at 0. That's not a big deal, okay? So now if you integrate the function So now if you try to integrate the function, negative infinity, infinity, absolute value of 1 over x dx. Again, if we do the calculus computations, this will be infinity, because this will give us, you need to split it as from negative infinity to 0, 0 infinity, then you do the integrals, you will get ln, that will give you infinity. That means that this area bounded between the curve and the x-axis is infinity. So again, what this says is that the function 1 over x is not absolutely integrable. So what examples do we have on absolutely integrable functions? Now it's clear, since our understanding for absolute integrability depends on areas and integrals of absolute values. So it is very clear that we need to draw some function whose area, we need to think of this, whose area with the x-axis is finite. So it's like, for example, imagine we draw a function like this. You say, okay, I have a function that's 1, for example, between two values like negative 1 and 1, and then it is 0, like this. So this is my function. So our function in this case is 1 when x is between negative 1 and 1, and it's 0 otherwise. And again, I don't need to mention this again and again. We don't care what happens at the negative 1 and 1, and you will see later. We already saw some stuff about it, that we're doing integrals. So whatever you have at those points doesn't change anything. But then we will see also what happens at the discontinuities, like what we did with the Dirichlet theorem with Fourier series. So if you look at this function now and you ask what's the area between this function and the x-axis, it's just this area, which is finite, which is 2, right? It's just the area of the rectangle. So in this case, f of x is absolutely integrable. Another example, and again, this is not a calculus course, so I'm not doing any calculus computations. You can go to calculus 2 if you like. But again, I just want to show you the idea behind all of this. If you look at the function, so now I'm taking the function f of x equals e to the minus absolute value of x. So what is e to the minus absolute value of x? That is e to the minus x when x is positive. Again, I don't care what happens at the equality, and x when x is negative. So if you draw it, e to the x when x is negative is like this. But then when x reaches 0, the function becomes e to the minus x, which is something like this, right? So now the question, what is this area bounded between the curve and the x-axis? If you do the integral, if you compute the integral from negative infinity to infinity, e to the minus absolute value of x dx, which is from negative infinity to 0, then from 0 to infinity, this will be finite. In fact, this will be exactly 2. This will be 1 plus 1, which is 2, which is finite. So in this case, you say, okay, so the function e to the minus absolute value of x is absolutely integrable. So this is the first thing. So again, I'm going back to the definition. So the definition says if you have an absolutely integrable function, right, then you define the Fourier transform this way. So the first thing, what do we mean by the absolute integrability? This is it. Okay, so we have like polynomials, the polynomials, none of the polynomials is absolutely integrable. Okay, so to have absolutely integrable functions, you need to guarantee that the area with the with the x-axis is finite. Okay, sorry, I deleted this. Okay. So this is the first comment. What do we mean by absolute integrable functions? Then the second thing, as we said while we were writing the definition, is what about periodic functions? So I'm saying now, if f is periodic, not 0, is f absolutely integrable? Of course, absolutely integrable on R. So now we're dealing, what do you mean by on R? From negative infinity to infinity. Now, when we talk about Fourier transform, the definition is the integral goes from negative infinity to infinity. So we're not integrating from negative pi to pi. We're not integrating from negative 1 to 1. We need to look at the whole real line from negative infinity to infinity. So now the idea, and you will see why I said not equal to 0. So if you have a periodic function. What's our understanding for periodic functions? I'm sure if we ask anyone to draw a periodic function, he would draw something. If you, for example, if he starts doing this, then he or she will have to copy paste, right? So this is our understanding for periodic function. Draw anything like x, then make it periodic, sine, cosine, anything. Think of anything that's periodic. Then ask yourself, what is the area between this periodic function and the x-axis, right? So just ask yourself this question. We know that periodic functions have the property, for example, if the period was 2L, so if you go from negative L to L, right? So we know that the area in this area, this part of the area, this is exactly identical to, let's change the color, blue. It is exactly this area. Then this area is exactly this area, and so on, right? So regardless of how small this red area is, it will be repeated infinitely many times, which means in fact that the integral from negative infinity to infinity for any periodic function is infinity. Okay, if you take any periodic function and you compute the integral from negative infinity absolute value, so you're talking about the area with the x-axis, and this area is composed of infinitely many parts when you look at the repetition of the periodic function. So basically avoiding zero. So if you look at the function zero, because you can look, if you like, at the zero function as a periodic function, it repeats itself over any interval you like. So this is the only periodic function that has a finite area with the x-axis, which is zero, and this is like the trivial function that we don't care about. Other than this trivial function, if you take any periodic function, it will not be absolutely integrable. So this is a very, very important thing, is that so periodic functions, again, other than the zero function, the trivial function, all of them are not absolutely integrable. This is a very nice remark to observe before we proceed to the Fourier analysis. So at this point, this is very, very crucial. So basically, you have functions. Just imagine you have a box containing all functions. Some of those functions are periodic. Some of them are not. Now, for periodic functions, some of them are absolutely integrable, but for periodic function, I want them to be absolutely integrable only on the interval negative LL. Some of them are not absolutely integrable. The same thing for the non-periodic functions. So some of them are absolutely integrable, but on the real line. Some of them are not. Now, for functions that are absolutely integrable, if they are periodic, so here, then we have the concept of Fourier series. Here, you don't have anything. Absolutely, if the function is absolutely integrable on the real line and it's not periodic, which is implicitly understood if the function is integrable, then you have something called Fourier transform. Okay, so this is like a classification of all functions. If you have them in one box in your mind and you need to think about them, you have a certain classification. Some of them go here to Fourier series, some of them go there to Fourier transform, provided absolute integrability. Okay, so this is the second comment I like to have. Then the third thing is, if you go back to the definition of the Fourier transform, you have the constant 1 over root 2 pi. So in our definition of f hat of w, we have f hat of w equals 1 over root 2 pi integral from negative infinity to infinity f of x e to the minus I x w dx, right? Now, what I like to say here is that the constant 1 over root 2 pi is here, I'm saying for convenience, okay? It's just for convenience. What do you mean by for convenience? I mean, if you open like 10 books, I'm sure you will see different definitions. Some of them, some people like to use the constant 1 over 2 pi. Some of them like to use the constant 1. So again, in some occasions, you will see, so in some other texts, you will see, for example, f hat of omega is 1 over 2 pi integral from negative infinity to infinity f of x e to the minus I omega x dx. That's very normal, okay? And you will see, in fact, just the integral from negative infinity to infinity f of x e to the minus I w x dx. This is very normal, and I'm sure, at least for communication engineering students, they will see one of those two definitions. Now, what is the difference between one definition and another? The main concept is still the same. The theory is still the same. The only difference is in what's built on these formulas. So if you use the formula with the root, like the one I will use, like our textbook, Kreisig, so then you have a certain form of the consequent formulas. If you use this one with 1 over 2 pi, you will see another form of the consequent formula. Very similar forms, but you will see differences in the constants. So please, if you go to other courses in this semester or other semesters, and you see another definition for the Fourier transform without the 1 over root 2 pi, don't be scared. They are the same, they play the same role, but you will have very little differences between one formula and another. And I hope I will remember to remind you at certain occasions, we will have certain formulas that I can tell you, look, if you use the root 2 pi, this is what you have. But if you use the other definitions with like 1 over 2 pi, you will have a different form, and so on. So I hope I will remember to mention this. The last thing that I like to mention here is that, so again, I'm looking back at the definition here at the Fourier transform before doing any example. The last thing is, if you look at this definition, forget the 1 over root 2 pi, but if you look at the integral from negative infinity to infinity f of x e to the minus I w x, I'm sure some of you have already remembered the CNs in the complex Fourier series. So now if we go back to the, so if f was periodic, if f is periodic of period 2 pi, we defined the Cn in the complex Fourier series by 1 over 2 pi integral from minus pi to pi f of x e to the minus I n x dx, right? So if you look at this definition and you look at the formula here, the box, the red box, f hat of w, you will see the two formulas very, very similar. Again, the 1 over 2 pi or the 1 over root, I consider them the same because, as we mentioned, you can use either constant. This is not a big deal. But if you look at the two integrals from negative infinity to infinity, from negative pi to pi, because the periodic functions, if you know the function on the interval negative pi to pi, then you can copy that part and paste it over the real line. So basically, the main block that you need to know about the periodic function is just the interval negative pi pi. Then look at the integrand. Both of them have f of x e to the minus I n x w x. Now, what's the difference between n and w? And by the way, the difference, okay, we'll mention this. The n in the complex Fourier series, the n is any integer, okay? So the n could be positive or negative numbers. Now, when we look at the Fourier transform, what is the omega? The omega could be any real number, sorry. So the w, sorry, here the w can be any real number. Now the math behind this, the n belongs to z, the w belongs to r. There is a lot of advanced math here in what's called locally compact abelian groups. It's a big topic in mathematics and harmonic analysis, so we're not going there anyway. But this is like another comparison between the Fourier transform and the complex Fourier series. And I will make sure to have one video just to show you how we can look at the Fourier transform as a consequence of this last Cn formula, the complex Fourier series. We will see how to obtain one from another, okay? Okay, so again, I wanted to show you these comments before we go to the examples. So back to our definition. So this is the definition of the Fourier transform. Let's see an example. So here we need to be very cautious, right? Because I can't say, for example, find the Fourier transform of the function x, because we've already seen that the function x here is not absolutely integrable. So you can't talk about its Fourier transform. You can't find the Fourier transform of 1 over x for the same reason. But you can find it for this function, the rectangular function. So I'm going to start with this easiest example, let's say. So my first example is, let's take the rectangular function 1 if x is between -1 and 1, 0 otherwise, and let's find f hat of omega. Okay, let's find f hat of omega. So we've already seen that the function is absolutely integrable, right? So we can just proceed to the definition. So what's the definition of f hat w? Is 1 over root 2 pi integral from negative infinity to infinity, f of x e to the minus omega x dx. Now in this example, my function is 0 outside the interval -1, 1. So basically, instead of integrating over negative infinity, you can just integrate from -1 to 1, and the function in this interval is 1. So you're just integrating negative e to the negative I omega x dx, and this is a very simple integral. It's just the e, but divided by the coefficient. And remember, we are integrating with respect to x, and the x values, I'm going to write it this way just to make sure you're following that these are the x values. Now what are these values? So this is 1 over root 2 pi. You substitute the 1, so that gives you e to the minus omega, minus you substitute the -1, you get e to the I omega over negative I w, which is 1 over root 2 pi. And now you start the simplifications, but we know these, right? What is e to the minus I w? It's cosine omega minus I sine omega. Then what is the e to the I omega? It is cosine omega plus I sine omega over negative omega. Now for us, the cosine is cancelled. Then what is left is just 1 over root 2 pi. Up you have minus 2 I sine omega. Down you have minus I omega. And now I can say cancel the negative with the negative, the I with the I, the 2 with the 2 with root 2. So basically what's left is just root 2 over pi sine omega over omega. Okay, so this is the Fourier transform. But if you look at these computations, these are very standard computations, very easy integrals. And again, this is not a calculus course. So the goal in this course is not to test you in calculus techniques. The integrals will be easy. And we will see how to use Fourier, in fact, to compute certain tough integrals. We will see that. So now if you look at this integral, I'm sure some of you have already seen that when you move from the second step to the third step, so at this point here, at this line exactly, we can't have omega as 0, right? We can't have it because you can divide by omega. So at this point we need to say, okay, so this is true when omega is not 0. Then what about omega equals 0? So now, unfortunately, when omega equals to 0, we have to compute it alone. So what is f hat of 0? We go back to the definition. So the definition is 1 over root 2 pi integral from negative infinity to infinity f of x e to the minus I omega x, but omega now is 0. So basically this is the integral from -1 to 1 because the function is 0 outside this interval, and the integrand is just 1. And what is this? This is exactly root 2 over pi. Fine? So in the end, what is f hat of omega? We have we will see two formulas. The first formula is that root 2 pi sine omega over omega. That's true when omega is not 0. And then you have root 2 over pi when omega is 0. So this is f hat of omega. Fine? So this is it. That's it. Now the idea in this particular example and in many other examples, if you look at, so again, we will have a comment here. Remark, all the time, if f from R to, so if you have a real valued function, if it is absolutely integrable, so we've already seen what we mean by integrable, absolutely integrable functions, like the one we have. So if the function is absolutely integrable, then f hat of omega is continuous, and I'm going to say regardless of f. So what do we mean by this statement? So this statement tells us, even if you start with a non-continuous function, so if your function is not continuous, its Fourier transform must be continuous. So all the time, if you start with an absolutely integrable function, and you have to start with that function because otherwise you can't have the Fourier transform. So if you start with an absolutely integrable function, you find its Fourier transform, then necessarily, this is what the statement says, okay? This is again a theorem in mathematical analysis, Fourier analysis. So if you start with an absolutely integrable function, its Fourier transform has to be continuous, regardless whether the function, the original function, is continuous or not. We don't care. The result is continuous. So in fact, if you look at our final result here, f hat of omega equals to this is a continuous function, because if you take the limit as omega approaches 0 of the first formula, you get the second one. So basically, what this remark says, in fact, for us, for mathematicians, it tells us that when you reach this point, although this is not true for omega equals 0, our understanding, because the Fourier transform is continuous, you don't need to compute the Fourier transform at omega equals 0. It's enough to take the limit of this. And in fact, we don't write it. It's just enough to write f hat of omega equals to this without saying anything, as long as we understand it, as long as it's in our minds. We don't need to say when omega equals 0, this is what we do, because we know that you need just to take the limit of this. Okay, so in like coming examples, I'm not going to compute what happens when omega equals 0, because the function is continuous there. Fine? Okay, so this is what the remark says. Okay, so this is our first example on Fourier transform. Let's have another example before seeing the inverse formula. So another example. Again, I need to have an absolutely integrable function. So this time I'm taking the function e to the minus absolute value of x, and let's find the Fourier transform. So I want to find f hat of omega, which is again this is a standard definition, okay? From negative infinity to infinity, f of x e to the minus I omega x, which is 1 over root 2 pi, integral from negative infinity to infinity. F of x is this formula, e to the minus omega x dx. But what is this? You need to split the integral, right? You need to split the integral. So this is from negative infinity to 0. Now this is e to the minus. What is the absolute value of x when x is negative from negative infinity to 0? It's negative x. So this becomes positive x, e to the minus I omega x dx, plus the integral from 0 to infinity, e to the minus x, e to the minus omega x dx. So this is 1 over 2 pi, integral from negative infinity to 0, e to the, what is the first integral? If you take x as a common factor, you will have 1 minus IW x dx plus, for the second integral, if you take again x as a common factor, you will have negative 1 minus I omega dx. It's better to write the x after 1 minus omega, but this is fine. Okay, so now you integrate this 1 over 2 pi. Then what's the first integral? These are very easy integrals. So this is 1 minus omega x over 1 minus I omega from negative infinity to 0 plus e to the minus 1 minus I omega x over minus 1 minus I omega from 0 to infinity. Okay. Now please, at this point again, we assume that we are not calculus students, we are experts in dealing with integrals. So this is not an improper integral lesson, okay? We assume we are professionals in doing improper integrals. So remember please, this is an improper integral. As long as you have infinity or negative infinity as one of your limits of the integral limits, this is called an improper integral. When you deal with improper integrals, remember, just to remind you, when you deal with an improper integral like this, if this limit is infinity, you need to change it to something else, and then you say limit b approaches infinity. Now, we assume we write this without writing it. So please, in my writing, and again, at the professional level, we don't need to write the details. We understand what's going on. So when you see this negative infinity, what do we mean? We mean, yes, we mean a b, and we mean the limit as b approaches negative infinity, and the same for that one. So I'm not going to write the limit this way unless we need it, okay? Unless we need it. So now what happens? So this becomes 1 over root 2 pi times, when you plug the 0, you get 1 over 1 minus IW minus, when you plug the negative infinity, you have a problem, right? But I'm leaving it empty, okay? So this is minus, so I'm going to plug here the negative infinity and see what happens. Then a plus, again, in the other bracket, you will have something when you plug the infinity, minus when you plug the 0, you will have 1 over negative 1 minus I omega, okay? So now here, I like, so let's leave some space there. So here, I like to show you the computations. What happens when you plug the negative infinity? So basically you have e to the minus to the 1 minus I omega x when x is negative infinity. Let's see what is this, okay? So first of all, again, my understanding for this is the limit as b approaches negative infinity, e to the minus I omega b, right? So this is, even if we don't write the limit, this is what's meant by e to the minus infinity or e to the infinity. This is what's meant by infinity. Infinity is not a number, it's just, we deal with infinity as just the limit. Okay, so what is this? This is the limit as b approaches negative infinity, e to the b, then e to the minus I omega b, right? Now, we know that when b approaches infinity, if you draw the function e to the x, so this is the function e to the x. So what does the left part tell you? It tells you that e to the minus infinity is 0. And again, when we say e to the minus infinity is 0, we mean the limit. We mean the limit as b approaches negative infinity, e to the b is 0. So basically, I know that this is 0. But what about this? Because when you deal with limits, if you have the limit of a product of two functions and the limit of the first one is 0, that doesn't mean the total limit is 0. And this can be explained by the very simple example, limit x approaches 0, x times 1 over x. If you look at the limit of this, it is 0. But when you multiply, the x gets cancelled and you get 1. So when you deal with limits, if the limit is 0 of the first function, it doesn't mean when you multiply you get 0. But here we will get 0 for the following reason. So I'm justifying now why is this going to be 0. Now what is this? This is limit b approaches negative infinity, e to the b times cosine omega b minus I sine omega b, right? Now what is this? This is 0 minus 0, which is 0. Now why is it 0? So when you multiply this with this, what happens? What happens is squeeze theorem, because we know that cosine omega b is always between negative 1 and 1. So when you multiply with e to the b, and since e is positive, so the inequality is preserved this way, this is what you have. Then you say, what's the limit as b approaches negative infinity? The two sides are zeros, so the middle term, this one, it has to be 0, right? So this is why when you multiply here the e with the cosine, the limit is 0, and the same reasoning applies for e to the b when multiplied with the sine. So this is why, okay, so these computations justify why when you substitute the negative infinity here, you get 0. And the same computations apply and justifies why when you have the positive infinity substituted in that quantity, you get 0, okay? Okay, so now we continue. What's this? Now it's just a matter of computations. So this is 1 over root 2 pi. You have 1 over 1 minus I omega, then plus 1 over 1 plus I omega. And now what you do is just a common denominator. And luckily, if you look at the two denominators, one of them is the conjugate of the other. So when you multiply them, you get 1 plus omega square. Then you have 2 upstairs. In the numerator, you will have 2. So this is my final answer. This is f hat of omega. Fine? This is f hat of omega. So if you compute the Fourier, the conclusion of this example, if you start with the function e to the negative absolute value of x, you try to compute the Fourier transform, this is what you get. Two different forms, completely different forms. Now, what's the relation? This is like the big question, like we did with the Fourier series. In the Fourier series, you start with a function, you find the Fourier series, then you start asking, what's the relation between the Fourier series and the original function? And now it's very natural to ask about the relation between the Fourier transform and the function, and that should be done, I think, in another video. I think this video should be stopped at this stage. Thank you.